The title of my presentation today is New Opportunities in Sustainable Nanomaterials. So in this talk, I will take you to the field of nanoscience and nanotechnology by showing a few slides. I'm sure there are a lot of young people. I asked Dr. Binoy, what is the composition of the group? So you have actually a mixed, attendees. So I will take you to the field of nanomaterials and its importance. Then I will take you what we are doing in Mahatma Gandhi University in the area of sustainable nanomaterials, extracting nano from sustainable resources. If you are really interested to look at our work, you can look at the website sabuthomas.com or iiucnn.mgu.ac.in, where you can see all our activities, all our patent publications, our infrastructure. Those who really wanted to collaborate with us, you can all interact with us. Those who want to use our facilities, you can definitely, visit us, interact with us. I'm going to show you my first slide. This is for the young students. What does nanotechnology mean to you? I'm showing a few slides to take you to the field of nanoscience and nanotechnology. Probably this slide is very familiar to all of you. You can see the lotus leaf. On the surface of the lotus leaf, you can see water droplets. Water droplets cannot form a film. It's actually forming a droplet with a high contact angle. And scientists and technologists look into this problem, why water forms droplet rather than forming a film. And we all know that water is highly hydrophilic. But the surface of the lotus leaf raise lots of questions. And I will show the next slide. You can see how the surface of lotus leaf looks like under high resolution electron microscope. You will see a cartoon here. If you examine the surface of lotus leaf under high resolution electron microscope, you will see large number of small hairy structures. These are all hairy structures you can see. These hairy structures are made of hydrocarbon, waxy materials. You cannot see this with the naked eye. If you look at the surface of a lotus leaf, you will see that extremely smooth, the naked eye. But if you examine under high resolution electron microscope, you will see millions of small hairy structures. They are all nanoscopic in the range of 15 to 20 nanometer size. They're all made of waxy material, hydrocarbons. Extremely non-polar. And water is actually polar. Water is polar. So this surface, these hairy structures do not like the water molecule. So there is a high contact angle between the surface and the water molecule. So water forms a droplet. Water actually hates the surface. Water is hydrophilic, the surface is hydrophobic. There are millions of nanoparticles on the surface of lotus leaf. Probably this is one of the finest examples I can show you from the nature to explain to you the nano effect, how nature engineers different surfaces. You all might be seeing the surfaces of the feather of many birds are very clean. And if you examine the surface, you can see when water falls on this leaf surface, it cannot form a film. You know, what does it do? It forms a droplet and rolls and get away from the surface. While rolling, you know, what do? These water droplets take away all the debris, all the dirt on the leaf surface. And the leaf surface looks extremely clean. Looking at this phenomena, this is called lotus effect. Looking at this phenomena, engineers have developed beautiful hydrophobic glasses. Probably there are now cars in Europe, in Japan, cars without wiper. Man has learned from nature and designed beautiful surfaces which are extremely hydrophobic. This is a super hydrophobic surface, a car without wiper. There are lots of nice super hydrophobic coating you can give on the surface of a glass. And as soon as the water falls on it, it will never form a film. It always exists as a droplet. And these droplets get away from the surface. And the surface is always clean, not hazy at all. I remember a few years ago, I went for a discussion meeting in Japan. It was actually a very rainy day, and I was picked up by the Toyota company. We had a cooperation with them. And then they sent a car to the airport. It was really interesting that this car had no wiper. And sunscreen never turned into hazy. So this is the way man has learned from nature and did something interesting. The surface of this glass has got hydrophobic CO2 coating, hydrophobic, see, there are lots of coating mechanisms, nano coating. So this is a very nice example where man has learned something from nature and made sophisticated technology. Another example I wanted to give you today is Geico. ഇതിലെ മലയാള ഉടുമ്പ്, നിങ്ങളെല്ലാം ഉടുമ്പിനെ പറ്റി കേട്ടു, ഉടുമ്പിന്റെ പിടിയെന്ന് കാർന്നമാർ പറയുന്നത് കേട്ട് കാണും. I have shown the picture of Geico. ഉടുമ്പിനെ പിടിച്ചുകൊണ്ട് ഉടുമ്പിനെ ഉപയോഗിച്ചുകൊണ്ട് ആൾക്കാർ പണ്ട് കള്ളന്മാരെ വീടിന്റെ മുകളിൽ കയറുമായിരുന്നു. ഉടുമ്പിന്റെ പിടി നിങ്ങൾ കേട്ട് കാണും. So scientists wanted to understand what is the secret of this. And if you examine under high resolution microscope, you will see that the palm of the gecko has millions of nanotubes. You can see this. This is the palm, and when you go into a nanoscale, you can see lots and lots of tubes. You know, when it moves on the surface, these nanotubes interact with the surface. And as a result of this, there could be strong adhesion between the surface and the palm. That is the secret of udumbine pidiyude secret. These are all non-covalent interactions. There are no hydrogen bonding, no electrostatic interactions, simple non-covalent interactions. These are millions of nanotubes. All these small forces add up, and you get very strong interactive forces. Again, looking at this, man has made something very interesting. You must have heard this Geico sticky tape. You see, a scanning electron microscopy image of 1 centimeter square section of a Geico sticky tape. And this is the technique of Superman, Spider-Man. Spider-Man go around using this tape. This is again a very fine example of nano technology from nature. You see how man has made, this is the Geico adhesive made by University of California, Berkeley scientists. And this is the palm of the Geico. See, looking at this palm, they made polypropylene nanotubes. And they sell this in the market as Geico type adhesive. Now I'm going to show you a couple of slides to indicate that nanotechnology is not new. How long have nanoparticles been used? Months, years, or centuries? I'm putting a question to you. The answer is nanotechnology is centuries old. I can show you fine examples for this. Pottery using nano-sized particles has been in use for thousands of years. If you look at Bible, I have a quotation of Bible. Moses took the golden calf they had made and burned it in the fire. Then he ground it into powder, scattered it on the water, and made the Israelis drink it. This is in Exodus 30-20. Probably you all must have read in the Bible that Moses led a long journey trying to escape from the King Pharaoh. It was a long journey for Israelis. There are no water, there are no food. So Israelis turned against Moses, turned against God. You know what Israelis did? They made a golden calf and started worshipping the golden calf. So Moses became very angry. You know what Moses did? Moses burned this calf at high temperature, dispersed in water, and asked all the Israelis to drink. You know, after drinking this, all people became okay. The gold nanoparticles can be suspended in water to make colloidal gold, used for centuries as a medical treatment that reportedly cleared the mind, increased intelligence, willpower, and balanced emotion. So I'm posing a question to all of you. Is Moses the father of nanotechnology? If you go to Europe, you can see fantastic cathedrals where you can see tinted glasses on the windows. And all these tinted glasses, you know, give rise to a variety of colors. Green, yellow, purple, violet. What is the secret of that? You see, these glasses were made with nanoparticles. They introduced nanoparticles. So these nanoparticles really provided fantastic colors to the glasses. So if you have an opportunity to go to Europe, if you see some old cathedrals, you can see beautiful tinted glasses. A fine example of nanotechnology, the Middle Age. Let me show you another example. If you are interested in history, you all must have read that in the Middle Ages, Muslim kings used to win many wars. You can see a war site here. Scientists wanted to understand why the Muslim kings won most of the wars. You know the reason? They had beautiful swords, knives, and they could kill the enemy very easily because of the sharp knife. You know what the Arabs did? Can you all see my slide?
Yes, this is fine.
Yes. Well, you know what the Arabs did? The Arabs used to buy steel from India. India was actually quite strong in metallurgy during Middle Ages. Arabs used to buy steel from India. And with a very special heat treatment, Arabs used to make fantastic knife, very sharp knife. You can see this article has come in Nature. This you can download free. Nature, volume 444. And you can see this when you examine this knife under electron microscope. You can see beautiful nanowires. That gave sharpness to this knife. So they could win most of the wars. You can see the knife used by the Arabs. This is called Damascus steel. Damascus steel was actually the steel they brought from India, and then they made very good heat treatment. Another important example is the chalice used by the Romans in the church. And these chalices were made of glass containing nanoparticles of gold and silver. I can show you a chalice is kept in British Museum. If you go to London, please visit this London Museum. You can see the color of the chalice changes. When illuminated from outside, it appears green. Now it's green. When illuminated from within the cup, it glows red. You see, now it's red. Fantastic color because the chalice is made of glass filled with nanoparticles of gold and silver. So we have lots and lots of examples. But I wanted to tell you that the technology is very old, but to understand the science, to understand the physics, understand the chemistry, we have to wait long. You could understand the chemistry and physics of nanoparticles last 40, 50 years. Before that, nobody could really understand the physics, understand the chemistry of this. You can see now people have developed, people synthesized nanoparticles of gold. You can see this is nanoparticles of gold with varying sizes, 20, 40, 60, 80. And you can see fantastic colors. Gold nanoparticles, if you vary the size, you have fantastic colors. We know the physics of these materials. So now you have blue gold, green gold, violet gold. So we can make fantastic colors by changing the particles. Let me now explain to you some of the milestones. Who are the contributors of nanoscience and nanotechnology? I think I should start with the fantastic experiment done by Michael Faraday. Michael Faraday introduced the colloidal gold samples of Royal Society. You can see the picture of Michael Faraday showing this colloidal gold nanoparticles in a test tube. Those who are really interested should read the documented literature, maybe the first documented literature on nanoscience and nanotechnology, Philosophical Transaction, Royal Society, 1857. And Michael Faraday was really excited when he made totally transparent nanoparticle giving fantastic colors. He never called it as nano, he called it as colloidal particles. It was Langmuir who established the existence of monolayers, layers of atoms or molecules, one atom thick. An Nobel Prize winner. It's a fantastic journal by American Chemical Society. Langmuir started to commemorate the contributions of the Nobel laureate, Langmuir. Albert Einstein gave a quantitative theory for the state of colloidal dispersion. It's very important that I should mention his name. You might ask, who is the father of nanoscience and nanotechnology? I would say Richard Feynman. I request all the youngsters to read Richard Feynman's talk when he received the Nobel Prize. Richard Feynman's groundbreaking talk, this is called groundbreaking talk, he delivered in 1959. So 1958, this is called groundbreaking talk. You know, he said there is plenty of room at the bottom. Many nano textbooks, you can see this quotation, there is plenty of room at the bottom. You know what did Richard say? Richard said, you can play with atoms and molecules and you can make a series of hierarchical structures. And he said the properties of these hierarchical structures could be controlled by the particle size, shape, and distribution. He got Nobel Prize in 1965, and Richard Feynman is considered to be the father of nanoscience and nanotechnology. You might be interested, who gave the name nanotechnology? The name nanotechnology came from a Japanese researcher from the University of Tokyo in 1974. He used the word to refer to production technology to get extra high accuracy for ultra fine dimensions. His name is Norio Taniguchi of University of Tokyo, who gave the name nanotechnology. So you will all understand that nanotechnology is much older. In the 5th century, people used to make a lot of things out of nano. But the science came very late. This is the case of rubber. If you trace the history of rubber, people started using rubber 15th, 16th, 17th century. But the understanding of chemistry of rubber came only in 1920 when the German Nobel laureate said, it's a macromolecule. So the chemistry of rubber, chemistry of polymers started in 1920. But technology started 15th century. People used to make fantastic things out of rubber. Let me also explain to you a few more inventions. Gerd Winning and Heinrich Rover from IBM. They made the first scanning tunneling microscope. So you can see atoms. You can play with atoms. With the invention of scanning tunneling microscopy, atomic force microscopy. I also wanted to, describe you another prize-winning work by Richard, Robert, and Harold. This is Harold. Harold was in our campus for about 2 weeks, interacting with the students and faculty. Harold is no more. He died. And their fantastic discovery of fullerene, C60, a very important nanomaterial. And I also wanted to tell you the work done by a Swedish scientist, Don Igler. Don Igler, what he did? Using the cantilever of scanning tunneling microscopy, Don could pick up xenon atoms, and he wrote the name of the company. You can see that next slide. He wrote IBM. These are all atoms. He picked up atom one by one. You imagine picking up atom with a cantilever. So he picked up xenon atom one by one, and he wrote his company's name, IBM. So now we are able to. This was happened in 1989. We are able to play with atoms using scanning tunneling microscopes. Fantastic discovery done by these IBM scientists. Then we also a few more discoveries. 1991 witnessed the invention of discovery of carbon nanotube. I request all the youngsters should read the Nature paper, the original paper of Ijima. 2 years ago, last year, Ijima was in Trivandrum for a macro symposium. He gave a fantastic lecture. It was the first time I met him. First time I'm meeting Ijima. Quantum dots were synthesized in 1983, a fantastic paper by Murray, Norris, and Babendi. All the youngsters should read this paper, a very classical paper, Journal of American Chemical Society in 1993. They made quantum dots of monodisperse cadmium sulfide, cadmium selenide, cadmium telluride. They said one can have fantastic colors by changing the size of these quantum dots. They absorb normal white light, give rise to fantastic different colors based on the size of these quantum dots. So this is a very original invention. Paper appeared in Journal of American Chemical Society. All the youngsters should read this paper. There are lots of discoveries taken by nano transistor, DNA motor, fuel cell prototype, nanoparticle embedded smart clothing. You can see this clothing is filled with nanoparticles. So smart textiles have become a very important area. There are lots of laboratories all over the world very active in smart textiles for soldiers, smart textiles for laboratories, smart textiles for cooking. This is stain-free. So this is a very big area, smart textiles. Textiles embedded with nanoparticles. If you have special textile embedded with nanoparticle, it can save the life of the soldiers in a warfare. All the toxic gases could be absorbed by nanoparticles. Nano solar cells, 2003. Solar cell, what we have now in our house top are very rigid, takes a lot of space. But now they're able to make very affordable type of, this type of, flexible, solar cells made of plastics filled with nanoparticles. You can use conducting polymers filled with nanoparticles. So I'm sure within a few years, all our conventional solar cells will be replaced by flexible solar cells. Another important discovery came in 2010. I'm sure all of my good friends know about the invention of graphene. My laboratory is also very active in graphene. Andrei Geim and Konstantin Novoselov, they actually made graphene in their laboratory using a Scotch tape. I request you to read the fantastic papers of Andrei Geim and Novoselov. Major invention in nanoscience and nanotechnology, 2010. I also wanted to show you one more invention, the Nobel Prize winning work. Jean-Pierre Sauvage from France, Fraser Stoddart and Bernard Feringa. They made nano engines, molecular machine. They shared the Nobel Prize in 2016. So a lot of fantastic discoveries taking place in the field of nanoscience and nanotechnology. Now let me tell you what is nanotechnology. A definition. Nanotechnology is nothing but the ability to work at the molecular level, atom by atom, to create large structures with a fundamentally new molecular organization. You can play with the size of nanoparticles. You can play with the shape of the nanoparticles. You can play with the distribution of nanoparticles. You can modify the structure. If you do that, you can have unusual novel properties. You know, gold is conducting, silver is conducting, but if you go to nano regime, they have no more conducting. You increase the band cap, so they have no more conducting. When you go to nano regime, you increase the surface area, or a high surface area. So you have unusual properties when you go to nano regime. That is why the father of nanotechnology said, there is plenty of space at the bottom. Even if you look at nanotechnology, nanotechnology touches all fields: automotive, sports, automotive field, sports field, chemical industry, medicine, communication devices, computer technology, information technology, all field nano has a very strong impact. You can see fantastic nanoparticles made in the laboratory: cadmium sulfide, cadmium selenide, gold nanoparticles, silver nanoparticles, fullerenes, dendrimers, carbon nanotubes, graphene, nanocellulose. Fantastic nanoparticles have been synthesized or extracted from natural sources. Let me also show you the nanotechnology global economic impact. The prediction is the coming 15-20 years, materials and materials processing, $340 billion business. Information technology, $300 billion business. Big business in the IT sector. Biotechnology and pharmaceutical science, $180 billion business. Catalysis and manufacturing, $100 billion. Aerospace, $70 billion business. Sustainability, water purification, energy, $45 billion. Healthcare, diagnostics, prosthetics, $30 billion. So every field of science and technology, Nano has a very strong. So with this background, I'm going to start my talk. I hope you've got some understanding about nanoscience and nanotechnology. I showed a few slides for the youngsters, for the students to understand this science. Now I'm going to show you some of my activities. We work on a variety of nanomaterials in my laboratory. We synthesize nanomaterials. We make carbon nanotubes. We make graphene. We make nanosilica. At the same time, we also extract nano from agricultural resources, sustainable resources. So I'm going to talk about how you can develop nanomaterials from sustainable resources, agricultural resources, and what are the opportunities. If you look at the waste worldwide, I have a good number here, 1.6 billion tons of agro waste being accumulated every year around the globe. It could be agriculture waste, it could be waste from the fish industry. What are these agro waste? It could be sugarcane bagasse, wheat bran, rice bran, corn, cob, food flour, or rice straw, jute, coir, or pineapple, hemp. So it could be variety of agro waste, variety of agro waste, variety of agro waste you can you have here. You see, fish industry, and so all this actually, if you don't utilize it, all these are getting wasted. All these are getting wasted. So one has to really utilize these materials for a variety of applications. Variety of applications. You see, if you look at the if you look at the if you look at the production of these materials, you see, wood is number one. Wood. So we have lots of work with many countries, especially Sweden. Sweden has a lot of wood. The 175,000 into 10⁻³ tons. Bamboo, cotton lint, jute, canaf, flax, sisal, lots of agricultural materials, waste materials. And what are the positive points of these agricultural waste materials? Environmentally benign material, friendly material. They are cost effective. Price is much cheaper than conventional materials. They are abundant. They are non-abrasive. There are lots and lots of positive attributes. Those who are really interested can read my old paper on carbohydrate polymers. So one can get the plant fibers from the leaf, from the stem, from the seed, or from the grass. See, if you look at our pineapple, you know, the beautiful pineapple leaf, you can extract, the fiber from the leaf. Flax, canaf, this is from the stem. If you look at the cotton, this is the seed. Coir also you get from the seed. Grass fibers, bamboo fibers, elephant grass. So you can have fibers from the bast, leaf, fruit. I have nice pictures of banana because we work with banana fiber quite a lot. Oil palm fiber, pineapple fiber, the leaf, oil from the seed. Now let me show you the relative price of this. It could be coir. See, if you take cotton as 100, cotton as the highest price because high content of cellulose. If you take cotton as 100, look at the relative price. They are actually quite cheap. And if you look at the mechanics of the properties of this material, particularly property divided by density, they are all having low density. If you look at the mechanical properties, tensile or Young's modulus or elongation at break, you will find that all these materials have fantastic properties, especially specific properties are very good, fantastic properties. What is the chemistry of this material, this cellulose? If you look at the chemistry, plant fibers basically has high content of cellulose. You can see the structure of cellulose. Fantastic structure. You have hydroxy groups. These hydroxy groups could be chemically modified. This is the structure of hemicellulose. So plant fibers are chemically lignocellulosic material. Lignin, cellulose, hemicellulose. I wanted to show you the hierarchical structure of the plant fiber. This is a plant cell. And if you take out a fiber, this fiber is actually macrofiber. And inside the macrofiber, you have many small fibers. We call it as a microfiber. This is a microfiber. And inside the microfiber, you have lots of nanofibers. So you can work in different length scales. You can work on, you can have macrofiber, microfiber, you can have nanofibers. So you can work in different length scales. That's the beauty of plant fiber. So my research group is now, what we are doing is we are extracting these nanocellulose from here. My laboratory, my PhD students, we are able to extract this nanocellulose. I'm going to show you what we are going to do, how we do the extraction process. This particular nanocellulose is an excellent platform for sustainable development. It's a very important point I want to tell you. It's a fantastic platform for sustainable development. They have high water holding capacity, high crystallinity, good strength, good density. They're fantastic material. And you can see this is the electron microscopic picture of nanocellulose. This is from banana fiber. My PhD students went to the banana plantation and we made this using steam explosion process. It looks like a gel, And if you examine under high resolution electron microscope, you can see nanocellulose here. You can prepare nanocellulose by a variety of techniques. I have mentioned here, high pressure homogenization process, super grinding process invented by the Japanese. You go to very low temperature and you go for a crushing, we call cryo crushing process. Acid hydrolysis we are doing in our laboratory. Steam explosion process, high intensity ultrasonication. So there are a large number of techniques by which you can make this fantastic material. You can see some of the, this is by super grinding. You grind them and finally you make nanocellulose. This is cryo crushing. You go to low temperature and go for a crushing. You see the nanocellulose made by a group of Alimdar and research group. You can go for a steam explosion process. This is being practiced in my laboratory. This is the microfiber. You subject to a steam explosion process, and then you can open up the whole cellulose, and you can see you can remove lignin hemicellulose. I'm going to show you the laboratory protocol, what we do in Mahatma Gandhi University. This is the waste agrofiber we collected from the agricultural waste. We go for an alkali treatment, and then we get a slurry. We go for a mild acid hydrolysis, or for a homogenization. Finally, what we get is cellulose nanofibers, diameter 29. It's a very simple process. You can do this in a BSc laboratory. It doesn't need any very complicated processing technique. And you can also do one more thing. You can make long nanocellulose. This is long nanocellulose. See? You can also make short nanocrystals. If you look at this long nanocellulose, you will see amorphous, crystalline, amorphous, crystalline, amorphous, crystalline regions exist. If you want to kill all the amorphous region, you know what you do? You use a strong acid. If you use a strong acid, all the amorphous regions could be dissolved out and you have nanocrystals. So my laboratory is able to make both nanocellulose and nanocrystals from agricultural waste materials. And the advantage of this material is, low cost. So if you're going for nano clay or nano carbon nanotube or nano graphene, quite expensive. So this is low cost, renewable resources, starting material is agricultural waste, regular shape, high axis ratio, and look at the modulus, 130 gigapascals. Usual polymers have a modulus of something like 2 or 3 gigapascals, and strength is 10 gigapascals. So they are all fantastic materials. I wanted to show you a very nice work of Mohammed and group from Europe. They made, by acid hydrolysis, they made beautiful nanocrystals from wood. This is a starting material from wood. They made plastic nanocrystals. These are all nanocrystals made by Mohammed and group. I will show you some of our processing protocol in my laboratory. You can see my PhD students collect fiber from the plantation and they do some processing in the laboratory. Then we have a steam explosion unit. After steam explosion, we go for a bleaching process. Acid hydrolysis using either strong acid or a mild acid. If you use a strong acid, you get nanocrystals. If you use a mild acid, you get long nanofibers. Mechanical agitation process. Finally, you get nanofibers. This is under electron microscope. I also wanted to show you the dynamics of the enrichment process. Look at the raw fiber that we get from the plantation has got 64.4% of cellulose. That is from banana. As you do steam explosion process, bleaching process, you see the cellulose content has gone up, almost 95, 96% cellulose. And lignin hemicellulose is ready. We are removing lignin hemicellulose by chemical hydrolysis. I wanted to show you some nice picture what we have made from banana stalk. My PhD student, he did a postdoc now in Israel, now he's in the US. You know what my PhD student did is he collected banana fiber from the banana plantation and subjected this to acid hydrolysis, and you beautifully made nanocrystals, cellulose nanocrystals. We have a long cooperation with Sweden. You can see nanofibers we have made from wood flower. My PhD student made some fibers from wood flower received from Sweden because we got a special variety of wood flower and we made nanofiber out of it. These are some of the AFM pictures. Look at our cooperation with Brazil. My PhD student made nanofiber from pineapple leaf. This is a FEACM picture. And then we have cooperated with Brazil and we made fantastic things out of it. I will show you in the coming slide. Another important point I want to discuss today is nanocellulose could be subject to a lot of chemical modification. And you can do a lot of chemistry on the surface. So this is a fantastic molecule for chemists. You can do tempo-mediated oxidation. And OH could be transformed into COH or CONA. You can do esterification reaction. You can do polymer grafting. You can do fluorescent labeling studies, and you can do fantastic fluorescent spectroscopy measurements. You can go for cationization reaction. You can go for silylation reaction. Yesterday, I have signed an agreement with Apollo Tires. We are going to work with him for 3 years to make use of nanocellulose to make tire tread. We are able to make high abrasion resistant tire tread. So Apollo is going to fund us for about 3 years. So yesterday we signed the agreement and we are going to get the funding from Apollo Tires using nanocellulose in tire engineering. This is a fantastic material for wound healing. We are working on wound healing. This is a fantastic material for water purification. You can make sensors, you can make EMI shielders. So nanocellulose is a very important base material for the manufacture of sophisticated, advanced devices. Let me show you how we have utilized for water purification process. A PhD student of mine right now in France, he made use of nanocellulose. I will show you a couple of slides. For water purification, what Dibu did is, Dibu made use of a tri-layer membrane. You see the bottom part is non-woven microfiber, and the middle part is electrospun nanofibers. And the top of this, he sprayed the nanocellulose dispersion. So this is the hydrophilic coating he has made on the top. I will show you the separation process. You see, Dibu has made nanocellulose from banana stalk, and he made a small chemistry in my laboratory, a green chemistry. He treated this with meltrum acid and introduced CO minus group on the surface of nanocellulose. Carboxylic group introduced by using meltrum acid. And then, you know what happened? When you use a dye, when you When you try to remove a dye, putting as a filter, this is absorption capacity of the dye, milligram per gram. You see the absorption capacity of the conventional filter. And this is the modified filter with nanocellulose. This is a commercial filter. Bottommost one is a commercial filter. This is the filter modified by chemically transformed nanocellulose with melt acid modification. So we have found that commercial filters could be transformed into high performance filters, high performing filters by using nanocellulose. And you might ask how this happens. You can see this is the commercial filter modified with the this is nanocellulose. These are the dyes absorbed, retained by the nanocellulose. And you might ask, what's the mechanism? You see, the mechanism is very simple. When you modify nanocellulose with carboxylic group, this is the COA minus, and this is the dye, crystal violet dye. There is electrostatic interaction between nanocellulose and crystal violet dye. So this is the way we have removed dyes from water. You know, the water is increasingly polluted because we have lots of textile companies, particularly in Tamil Nadu. And lot of dyes go into the river stream. And river water is increasingly polluted. So we have shown that you can make this sort of membrane. If you see the work of Professor Ma from Japan, Ma also did something similar. You know, if you look at Ma's work, this is a conventional filter that you get from the market. Professor Ma modified the filter with the nanocellulose. You can see the efficiency has increased. We also try to remove suspended particle in water. You know, the water has lots of suspended particles. It could be nanoparticles, microparticles. So what we did is we tried to remove suspended particle in water through these nanocellulose filters. You can see after filtration, all the particles are retained by the filter, top of the filter. This is the bottom part of the filter. See, our filter was so efficient, removing all the suspended particles. You can see this picture. Before removing the water, suspended particle, the solution was completely opaque. This is a feed solution, completely opaque, black in color. After filtration, you see the water is very clean. We could remove all the suspended particle and you have the almost 100% transmittance. I wanted to show you some work of this, Finnish group, Korhonen group. You know, Korhonen group, you know what they did, the very interesting work they did. They made nanocellulose from sisal plants, and they made an aerogel. You can see this is the aerogel made by Korhonen group in Finland. You know, then what they did, they made the surface of nanocellulose. In the beginning, I told you the Japanese car without wiper. You know, they made use of titanium dioxide to make this surface extremely hydrophobic. Probably you all know that now our seawater is increasingly polluted because of the oil leakage from the ship. For Korhonen group, you know what they did? They made this nanocellulose aerogel and sprinkled the aerogel in seawater. And this aerogel is able to absorb all the oil because the surface is hydrophobic. It cannot take the water. Water forms a droplet, just like lotus effect, you see. It takes away all the oil from the sea. And you can squeeze out the oil or you can burn the oil. So this is a way we can clean the seawater using nanocellulose aerogel. And you can see the coating they have given on the surface of nanocellulose. This coating is very important because to make the nanocellulose surface hydrophobic, then only it can absorb oil. This is an excellent material. Nanocellulose is an excellent material for removing different types of metal nanoparticles in water. If you look at India, many parts of India, the drinking water is contaminated with high quantity of metals. It could be chromium, it could be zinc, or it could be copper. And you can use nanocellulose platform derived from agricultural waste as a filter to remove chromium. You can see chromium absorption. You can see this graph, chromium absorption using nanocellulose platform. You can have 90 milligram per gram. You can reach slightly more than that. This is a beautiful comparison of absorption. Straw fiber, straw fiber is also a good material for removing nickel, cadmium, or lead. You can see this is raw fiber. This is cellulose fiber. This is nanocellulose. Look at this. If you go for nanocellulose, the absorption efficiency is quite high. Absorption efficiency is very close to 100. You can also remove bacteria and viruses. Now we are all facing the problem of corona pandemic, coronavirus. You can also make use of nanocellulose platform derived from agro waste to remove bacteria and virus. You can see these viruses could be easily removed, bacteria could be removed. Bacteria are bigger in size, so when you engineer this nanocellulose filter, since bacteria is bigger in size, they could be retained by a size exclusion principle. But if you want to catch virus, coronavirus is very small in the range of nanometer, 100 nanometer. If you want to catch up viruses, then you have to chemically modify the nanocellulose. You can put lots of chemistry on the surface. You can have amine group you can put into the surface of nanocellulose, and you can catch viruses. So you can remove viruses, bacteria from air or from water using nanocellulose filters. You can see a gentleman suffering from high degree of burning. His face is completely burned. And you can see his face is covered with nanocellulose scaffold. And this nanocellulose scaffold is extremely porous so that the tissues can grow quite rapidly. So it's a fantastic scaffolding material that you derive from agricultural waste. I wanted to show you something interesting we have done with Brazil. Polyurethane cellulose nanocomposites. My student went to Brazil. We made nanocellulose from pineapple leaf. And then he went to Brazil and stayed for about 2 years. And Brazilian group made a fantastic material, polyurethane material. They made in the laboratory hot wall, medical grade polyurethane. And then we introduced nanocellulose from India, from my laboratory, 2%, 5%, 10%. Look at the property profile. Polyurethane made by Brazilian group had a strength of 17.5, modulus of 37.5. The value was a little bit smaller, because for this sort of application, we need high strength. So we thought of putting nanocellulose. Look at 5% of nanocellulose, 37.5 became 992, a quantum jump in modulus. The Brazilian collaborator, Daniel, was very happy to see the result. And eventually what we have made is, we have made nanocellulose polyurethane prosthetic hot wall. We have a lot of series of patents in Brazil. And the Brazilian hospital also cooperated with us. We made beautiful hot wall using nanocellulose derived from pineapple leaf fiber and polyurethane. We also published a series of papers. Let me also tell you that nanocellulose derived from plants are good material for wound healing application. Maybe a couple of examples. I wanted to show you the work done by the Spanish group, Sebastian. You know what Sebastian did? Sebastian made nanocellulose aerogel. Very easy to manufacture. You go for a freeze drying. And Sebastian then introduced antibiotic into this aerogel. And look at the sustained release of antibiotic. Sebastian showed that nanocellulose platform is a fantastic base material for sustained release of antibiotics. We have some cooperation with Sebastian's group. I also wanted to show you the nice work of Liu from China. You know what Professor Liu did is, Lou made a combination of nanocellulose and collagen, and he made a composite collagen, aerogel collagen. He said that this is extremely porous. And he said that this is a fantastic material for cell proliferation, wound healing. Wound could be easily healed because it's extremely porous. And since he mixed nanocellulose collagen, compatibility was very high compatibility. And the porosity is 95%. You know, if you want to make something for tissue growth, we need highly porous structure, then only the tissue can grow. So Professor Lou is very active in this field. I also wanted to tell you that there are a lot of commercial membranes made from acrylonitrile, made from different types of polymers. If you look at the commercial membranes, these commercial membranes have a shortcoming of poor mechanics. Look at this sustain curve. The mechanics are very poor, commercial membrane. But if you give a coating on the top or the bottom surface, look at the coating of the nanocellulose, one side coating, you see the mechanics, the mechanical properties improve dramatically with one side coating. If you give coating on both sides of the membrane, mechanical properties are further improved. So nanocellulose is a very good reinforcing material for commercial membranes. Their strength could be increased. I wanted to show you something we did using COVID time. We proposed a few projects. I wanted to show you one project we submitted to India-US program, BST NSF program. You know, what we have done is we proposed a new mask. You know, this mask is 6-layer mask. What we proposed is a 3-layer mask. The outer layer is made of polyester fabric coated with a polyelectrolyte that can repel coronavirus. Coronavirus cannot come, you know, this coronavirus will repel. It's anti-adhesive layer. And the middle layer is made of nylon, electrospun nylon, filled with positively charged nanocellulose and some curcumin. This is a middle layer. And the middle layer can, if at all some virus is getting inside, this middle layer can kill the virus because it has a positive charge. The virus has an envelope of protein which is negative. And the innermost layer is made of cotton, which is very close to your mouth. So you should have good wearing comfort. So this is the protocol we have made for the NSF program. You can see this is made of polyester outer layer, which can drive away the coronavirus. This is the middle layer, which can kill the virus. This is the innermost layer, which is made of cotton. Anyway, I don't want to go into much details. I also want to tell you that this is a fantastic material for sensors. You can make sensors. Maybe I can show you one slide with lack of time because it's going to be 1 hour. You can make beautiful sensors. I want to show you one slide here. This is actually nanocellulose suspension made from pineapple leaf fiber. See, this is 0 hour, after 24 hours, no settling. Beautiful dispersion. Look at carbon nanotube. Carbon nanotube in water, you know, after 24 hours, all the carbon nanotubes settle down. Unstable dispersion. You can see theta potential here. But if you mix carbon nanotube and nanocellulose together, you look at the stability. Fantastic stability. So my research group is very active in hybridizing nanocellulose with carbon nanotube, nanocellulose with graphene. Maybe I can show you 1 or 2 slides. Look at the conductivity as a function of CND concentration. This is with natural rubber. So we made conductive rubbers. If you use only CND, you have percolation somewhere over here. You have to add 6% of CND and you have a percolation process. If you have a combination of CND and nanocellulose together, look at the percolation here. See, you get percolation at 1.5 volume percent of carbon nanotube. So we made fantastic electrically conductive natural rubber material, combining nanocellulose and CNT. We are also able to make fantastic material for energy storage applications. I wanted to show you the work of Professor Wang in China. You know what Professor Wang did is, Professor Wang synthesized aerogel from cellulose made from sisal fiber. And then he went for pyrolysis at 900 degrees Celsius. So you know what Professor Wang did is, he made extremely porous aerogel, carbon he made. He found that this is a fantastic material for electrodes, particularly for anode material in lithium-ion batteries. So Professor Wang is an expert in manufacture of anode material for lithium, and he said it's a fantastic material because it's extremely porous. So there's a lot of interaction between electrolyte and the anode. I will show you maybe a couple of slides, then I will, a few slides, then I will wind up. I'll show you some of our recent work, which we published in ACS. My PhD student Deepu made nanocellulose from pineapple leaf fiber. Then he went for in situ polymerization process, and he made conducting nanocellulose paper. You can see the complete protocol we have made. You can see the nanocellulose suspension we have made from banana fiber, went for in situ polymerization of aniline, vacuum filtration, cold compression. You know what he has made? He has made thin, conductive nanocellulose paper. Fantastic material. And this is very good for EMI shielding applications. If you look at our mobile phone, they have an EMI shielder, metallic EMI shielder. And we have shown them that we can make beautiful, lightweight EMI shielders from plant fibers. You can replace the metallic EMI shielders with plant-based EMI shielders. See, look at, you can get 16 dB EMI shielding. We are also into chitin chitosan. I have a few PhD programs going on with chitin, nanochitin. You know what we do? This is a beautiful structure of nanochitin, the NHCO-CH3 group, chitosan, and we make chitin. Very simple process. We collect the shell of the prawn or crab, and then we do a simple acid washing in my laboratory. Look at the nano viscase we have made. Simple process. I will show you just a couple of nice work. This is chitin molecule, nanochitin. If you do a small chemistry on this chitin surface, you can make a lot of long hydrophobic groups. Look at this, they're all long hydrophobic groups. If you do a small chemistry on the nanochitin becomes extremely hydrophobic. You can see this is the neat nanochitin, this is hydrophilic. But if you put lots of hydrophobic groups, arms on the nanochitin, it becomes hydrophobic. So this is an excellent additive for oil. Excellent additive for oil. So one can make hydrophobic nanochitin as an additive for oil, structuring the oil. We also made filters. You know, my PhD student, this is a cooperation with Slovenia. My PhD student made PVDF nanochitin, PVDF 22.3% with the nanochitin combination. Once you have a combination of PVDF and nanochitin, he found that dye can be easily removed. You can see this is a PVDF alone. Dye removal is 23.3%. If you have PVDF and chitin from the crab shell, you see the removal efficiency is 88.9%. So we made fantastic filters combining chitin and PVDF. PVDF is a synthetic material. The combination gave fantastic results. Finally, I wanted to tell you that we are also into waste, starch. A lot of agricultural waste. If you go to agricultural field, you collect all the waste material. We are not touching the food sector. We are only collecting the waste. Starch is a fantastic material. Cassava waste you can collect. And you see, If you do a acid washing, you can make nano starch. This is nano starch particle. This is made from maize. You can make nano starch from tapioca or from potato. I will show you one work we did with my PhD student. We have taken natural rubber latex. Look at rubber latex and we made film. This is natural rubber. Strength of natural rubber. If you put nanoscopic starch, nano starch into natural rubber, look at the strength goes to 14 megapascals and modulus goes up. So we have shown that the waste starch material from agriculture area could be collected and transformed into nano. Very good additive for plastics and plastics. And my concluding remark is quite simple. Agro waste could be transformed into advanced functional green nanomaterials. Nano from lignocellulosic materials, you can make beautiful nanocellulose fibers in this case, and they are fantastic applications. You can make EMI shield layers, you can make energy storage, wound healing, water filtration, reinforcement. From seafood waste, you can make nanochitin, fantastic material for water purification, heavy metal removal. From agriculture starch, waste starch, you can make nano starch, good reinforcing material. And we have to preserve our globe for the future generations. So we have to have the philosophy of zero waste. And we become a zero waste planet. This is my question to all my young people. And thank you very much for patient hearing. And I would like to acknowledge my co-workers. They worked very hard in my laboratory. Marine, Hannah, Anish, lots of people contributed. Government funding, particularly Professor Siena Rao for the generous funding from Nano Mission. He really supported us. I'm extremely thankful to Professor Siena Rao. He's in Bangalore. Funding is from CSAR, DBT, you can see. International funding from France, from Sweden, from Slovenia, the World Academy of Science from Brazil, DuPont, United States, General Cables, US, Surface Street, Czech. Industrial funding from MRF, with Apollo, we enter into a cooperation. We are going to start the 3 years work with them now. In the past, we did a lot of work with them with clay. You can see my collaborators worldwide, Brazil, Sweden, France, South Africa, Slovenia, Germany. This is my group in chemistry. Our visitor from France, Yves has come, so we are a group photograph. This is my group in nanoscience and nanotechnology. You can see my, I'm director of the Nano Center. It's me. Now, as the director of the center. You can see our visitors from Malaysia. We have students from Africa. Those who have not come to our campus, most welcome to Mahatma Gandhi University campus. And we are organizing an international conference on 100 years of macromolecular science. I said the understanding of the chemistry of macromolecules were revealed sometime in 1920 by a German chemist. Now it's 100 years now old, so we are celebrating 100 years of polymer science, macromolecular science in the campus, November 11, 12, and 13. And we are organizing another face-to-face meeting, an international conference on nanomaterials from April 9 to 11. I'm also the editor of Nanostructures and Nano Object by Elsevier. The current site score is 5.6. So those who work in nanostructures and nano objects can submit your articles to, those who work on nanomaterial can submit your article to this journal. This is a conventional, traditional journal, no fee, not open access. So you are welcome to present your paper. So thank you very much for your patient hearing. I will be very glad to address some of your questions. Thank you.
Professor Sabu Thomas and Babu Joseph here.
Hello, sir.
I am very much impressed by the excellent presentation you have made. I have heard 1 or 2 lectures on nanotechnology before, but this is the first time that I am exposed to the large variety of applications, potential applications and ongoing applications of this magic world of nanomaterials. I have a doubt. I have one or two ideas to share with you. One is that I have noticed that we have been talking about nano size fibers and so on. Uh, is it likely that the tissues of our body, biological tissues, is there a possibility of naturally occurring biological tissue being made of nanofibers? Cells being arranged as nanotubes and so on in our body. Has any study been undertaken?
This is actually a very interesting question by Professor Babu Joseph. You see, you can do 3D printing using nanostructures. So this is our future ambitious program. We are building up a 3D printer, bioprinting. So you can do printing of organs, combining nano with tissues. So it's possible. Tissue regeneration, tissue printing is possible. And Sujitra Tinal Institute actually is doing, they have a very excellent bioprinter. You can do organ printing using nanoparticles and tissues. It's a very emerging area. Lots of people work across different laboratories. In China, they're very active. In the US also, they're very active in bioprinting. It's a very emerging area. And electrospinning is also a very fantastic area where we are doing electrospinning doesn't need much of cost. We have a series of electrospinning in our laboratory, but we are trying to have the bioprinting very soon in our laboratory so that we can, work on organs. There's a massive area coming up. Very interesting question.
Another follow-up question. Uh, I, at present, there are a lot of applications of nanoscience at the laboratory level, product development and so on. What are the difficulties in scaling up this work to the industrial level? Are there any projects uh, which will enable us to interface laboratory work with the industries?
Yeah, you see what we have done, Professor Babu Joseph. What we have done in the campus, we have set up a company in the campus now under RUSA funding, and we are starting the commercial production of nanocellulose first in the country in Mahatma University campus. Nanocellulose, we are going to have maybe 50 kilogram capacity nano plant is coming over here. Extracting nano from agro waste. This plant we are going to set up. And if you look at Indian, we have lots of interesting work in many laboratories. I think we have to work with companies, or you need to have incubation facilities, show to big companies that there are a lot of possibilities. So nanocellulose is one of the amazing nanostructured material because it is renewable resources, starting material renewable resources. So this is, we are going to start in the campus. We have also fantastic idea to make nano chitin, nano starch. All these biological materials are beautiful, biocompatible, renewable resources. This is our first ambition, starting a company. We got 50 crores from BUSA. Of the 50 crores, 15 crores of funding is for the company. So we are in the process of the building has come. And I'm sure within 6 months, we will start the nanocellulose manufacturing in the campus.
Oh, that will be wonderful.
Yes, we have set up a company already. Yes. And then there are a lot of spin-off. This company will, promote a lot of spin-off actually. My former coworker, I also presented some of his work, especially chitin. He started a company now. So I think lots of youngsters, rather than going for a conventional job, they should start companies.
Right.
So companies they should start. And I'm also promoting a lot of startup. We have an incubation facility. Whoever is an idea, they can come to MGU campus and we will provide them infrastructure, for startup companies.
Okay, quite impressive.
Very, very important question, Professor Babu Joseph.
Thank you so much. Once again, I wish to record my appreciation, not only for your lecture, but for the wonderful world of technology that you are opening up. I foresee great potential for this field in Kerala itself under your leadership.
Yes. Yes. Thank you, Professor Babu Sebastian. Yes. Professor Babu Joseph, yes.
Dr. Sabathomas, I see a question from Hannah that's by messaged. What are the risks involved in nanotechnological explorations? Is it harmful to humans at some point at least? Yeah.
Yeah, this is a very important question. Many nanoparticles are harmful to body because nanoparticles are so small, it can break all the barriers and go everywhere. Particularly, I will show you a small example. We were working with the electrospun PCL. PCL is a very interesting polymer, biocompatible, FDA-approved polymer, polycaprolactone. So we were making wound healing patches, and we also introduced a little bit of zinc oxide. Zinc oxide is a very interesting material, but we found that we just added 1% first. Beautiful, very good wound healing, no toxicity at all, 50 nanometer size. We slightly increased the zinc oxide content to 2%. Massive depth of tissues. So nanoparticle size, shape, distribution, loading are very important. So one has to be extremely careful when you deal with nanoparticles. We need to have a thorough understanding about the interaction of nanoparticles with the body tissues. I'll tell you another story. We had a very strong cooperation with Strasbourg. For the last, one of the high-ranking universities in France. In the beginning, when we started working carbon nanotube, we used to do a lot of work in France, mixing carbon nanotube. But after 5 years, they stopped all the carbon nanotube mixing in French laboratories because they found that carbon nanotube is extremely toxic. So many nanomaterials are found to be quite toxic. So we have to be very careful dealing with nanoparticles. We have to use multiple masks and gloves. Once nanoparticles are in your body, very dangerous. So this is a very important aspect to be studied. And I request all my students and fellow colleagues, when you use nanoparticle, please take extra care. Students should not be allowed to expose to nanoparticles. They have to wear multiple masks and gloves. All laboratory practices have to be strictly followed. Otherwise, once they get into your body, it cannot be easily excreted. It can go to brain, it can go to liver, it can go anywhere. There are very tiny particles. So you have to handle with them very carefully.
Any other questions? Yes, please.
Hello,
proceed.
sir. Myself, Linsa, student of St. Xavier's College, Tumba.
Very good, Linsa. Yeah.
Sir, first of all, thank you so much for such a wonderful session. So you talked about various applications of nanomaterials. What I would like to ask is that could you please point out one or two challenges that are faced in this particular field at present?
You see, the main challenge in nanoparticle, my group is using nanoparticle as a reinforcing material in polymers. See, work with the tire company. See, I have a cooperation. I signed the agreement yesterday with Apollo Tires. They are funding us for 3 years as a reinforcing material. Right now, if you look at tire, the reinforcing material for tire is carbon black. That is why all tires are black. You don't have white tires, green tires, no. But now, we said we can remove carbon black. Carbon black is also very dangerous to health, mixing carbon black. We said we can try with nanocellulose. But the challenge there is how to disperse these nanoparticles beautifully in the polymer matrix. The surface is so active. It is different from the bulk surface because the surface is very active because you are working in the nano regime. The surface is active like atomic surfaces. So they have a tendency to aggregate because surface is so active. They try to aggregate because they wanted to reduce the surface free energy. So mixing nanoparticle is a big challenge. You make nanocellulose from wood, from a chop-down approach. You clean, you get nanoparticles. But the nanoparticles that you get, they accumulate. So you need to have lots of chemistry on the surfaces to suppress agglomeration. This is a very big challenge. Second challenge is nano has dramatic application in health sector. Nanoparticle assisted drug delivery, nanoparticle assisted scaffold material. Again, as Dr. Hanna indicated, she asked a question. Long-term effect has to be studied thoroughly because they could be deleterious to your body after a certain period of time. You do not know. That's again a very big challenge in using nano for medical applications. So these are the two challenges I see in the range of nanoscience and nanotechnology, but the scope is enormous. Potential is enormous. We cannot stop working on nanoscience. We should go working in nanoscience, but we have to take all precautionary measures.
Sir, thank you for the informative talk, sir. Very interesting talk. Sir, whether the climatic conditions affect the properties of cellulose from agro waste? We are collecting from different places, so
It's a very, very interesting question. You know, the wood flower that we get, that is why in the course of my lecture, we have collected some wood flower from Sweden and we did some measurements here. See, the nanocellulose that you get from the agriculture sector, it is affected by the climatic conditions, affected by the nature of plant. Even the same plant, the nano you get from the different regions of plant could be different. It's a very interesting question. So whenever you extract nano from agro waste, we have to do a thorough investigation. What is the diameter? What is the size? So it is affected by the locality, the geographical location where you have the plant, the season. Even the same plant, you have different, structures when you extract from the trunk, or from the branches, etc., etc. So very interesting question. So what you do is, when you characterize, when you manufacture them, you have to really characterize them very thoroughly. Yes, this is a very important question.
thank you, sir.
Yes.
Next, Sebastian. Okay, Professor Sebastian, Dr. Sebastian, we are not able to hear you. Either
Or you can type your question in the chat box.
It is there, so I am reading it for you. Is there a way to get rid of the heavy metal after it is bound to cellulose?
You see, we make cellulose membrane, and then you can use it as a filter to remove heavy metals. Once the heavy metals are trapped in the cellulose, you can desorb them. You can desorb this metal, and then you can reuse this filter again and again. They're almost a similar absorption capacity. So use a filter. This filter remove these, heavy metals. Then you can use a solvent which can desorb these metals. And these metals could be eventually, destroyed, or it could be transformed. And you can reuse the filter again. This is a protocol we have done. Similarly, dyes. You see, our water bodies are increasingly polluted due to the dyes from textile industry, because we need a lot of dyes for coloring our clothes and the textile. A lot of contamination. So you use the filter, you remove the dye, the dye is trapped onto the nanocellulose filter, and then you have to have an etching solvent, remove the dye, reuse the filter. This is a protocol we have suggested and we have used in the laboratory.
Father Binoy, can I ask a question?
Oh, sure. Dr. Joe Jacob, great joining us from Newman College. Kindly propose.
Yeah. Thanks a lot for your very informative and very an excellent talk. And also for thank you for the continued work which you are doing there. There are lots. And first question, I'm not sure whether you have explained it, but somehow I might have missed. So the question is like you mentioned that the nano materials are having different properties than the bulk materials. So what may be the exact cause? Is there any specific reason which we can cite why a nano-sized
you see, the issue with nano is
with the same composition as a
you see the composition is same. What happens is when you go to the nanoscopic regime, I would say you have atomic surfaces. You have lots of atoms on the surfaces. If you look at a bulk material, you don't have an atomic surface. It is all hidden actually. Yeah, so that is the reason why nanomaterials behave quite differently. The surface is very, very active. Surface area, surface to volume ratio is very high. Fantastic surfaces. We have prepared surfaces of, nanoparticle surface area 2000 meters square per gram. Look at 2000 meters square per gram surface area. It's a fantastic surface area. So you deal with atomic surfaces. Atomic surfaces so different from the bulk. That is why the surfaces behave extremely different from the bulk. A good example is easy if you look at gold. Gold color is golden color. You go to nano regime of gold nanoparticles of different sizes, then you change completely the color. You change completely the conductivity profile, you increase the band gap. So there are a lot of changes taking place in the optical properties, the surface properties. So these are the reasons why the surfaces behave quite differently.
Thank you, sir. Can I ask one more question?
Yes.
Yeah, this is connected with maybe a little controversy, kind of regarding homeo medicines. I heard somewhere that the homeo doctors arguing that because in homeopathy, what they do for the medicine is they dilute the medicine, and
They dilute.
the argument
Yes,
is that
yes. Extreme dilute.
It becomes more potent. So the scientific kind of theory which people put forward is that when it becomes nano, the material, the medicine material is in the nano size, then it has potential therapeutic kind of properties. Is it true from the scientific background?
You see, what we have done is a doctor, homeo doctor, who came to our laboratory. He's right now a senior professor in a university in Tamil Nadu. He came to our laboratory and he examined a series of homeo samples with extreme dilution using high resolution transmission electron microscope. We have a powerful high resolution transmission electron microscope in our laboratory. Interestingly, we could notice large number of nanoparticles in that extremely diluted samples. So I have a very strong feeling that the activity of all this homeo medicine could be the presence of these tiny nanoparticles. We could see lots and lots of nanoparticles in the samples given by this homeo doctor. This could be, but still we need to do lots of further work. It's a very interesting question you asked. So I have a strong feeling that homeo medicine at the extreme dilution. Many people, many of my friends, they believe that it's pseudoscience, but I reject such ideas. Homeo has a very strong point. And I've seen fantastic results from homeo medicine. We had a very nice talk, last week, which involved allopathy doctors, homeo doctors, siddha doctors, Unani doctors. It's a fantastic discussion. Our group meeting, I acted as a moderator. There were doctors from Europe, from India. They started at 5 o'clock, and we thought of having the meeting for 2 o'clock, 2 hours, but it went up to 10:15. So there is a fantastic science there. And we believe that it is due to the presence of these tiny nanoparticles. Very interesting question. I hope we will be able to. We are now writing a paper jointly with this homeo doctor. It's not at all pseudoscience. And many of my good friends, medical doctors, they objected even organizing this meeting in the camp. They said they are all pseudo people. It's not pseudo. They are all fantastic science. You see the challenge faced by the German scientist, when he said macromolecule rubbers are macromolecules. And many German chemists said this Staudinger is a pseudo chemist. Ultimately, he got Nobel Prize, So this is the viewpoint of many people. Many people say homeo is pseudo and siddha is pseudo and Ayurveda is pseudo. No, these are all fantastic sciences. We need to understand the subject. So I have a very strong belief in homeo. Very good question.
Over to Samantha. I see a couple of questions more. If done with Dr. Joy Jacob, over to Samantha. Or there is one more question. Yeah. You may ask in person.
Sir, my name is Samantha Sam.
Yes.
I am from Sacred Hearts College. I would like to know that this whether it is toxic. The nanoparticles that is extracted from Cuscuta epithelium, is it very toxic if we use with our hands? If it come in contact with our hands, is it very toxic or not?
Which nanoparticle you mean?
Nanoparticles extracted from Cuscuta epithelium.
Okay. You see, the nanoparticle is extracted from agricultural waste. They're not toxic at all. Provided, see, we use, if you use acid, there could be some acid residues. So you have to remove all these acid residues, by washing with water. If you do that, if you do a systematic protocol in extracting nano from agricultural waste, they are not at all toxic. You can use it for biomedical applications. That is the
We
beauty of.
extracted using acid hydrolysis.
Then you have to remove all the acid. Using water. We can remove that.
Okay.
All the residual acid could be removed. Then it's not at all toxic. But you can also use, now people are developing biological treatment. You can use microbes to eat away lignin hemicellulose. That technology is being developed. Yeah. So people are trying to have more eco-friendly techniques rather than using acid. Your point is correct. Using acid is not very eco-friendly, but you can get rid of all the acid residues from the nanocellulose. No issue at all.
Oh, thank you,
You use a
sir.
lot of dialysis. You use a lot of dialysis to remove that. Very interesting question.
Okay. I think we can engage in maybe 2 more participants with your questions because I know it's running short of time. Or Professor Sabu Thomas must also be busy. Well, I see if you have messaged, you may ask the questions.
Hello, sir. Hello,
Yes.
sir.
Yes, please.
Sir, I am Japsi. I am also from St. Xavier's College, Tumba, Trivandrum.
Very good.
Okay, sir, this is almost a general question. So my question is, can you tell us some important areas of nanotechnology which are given more demand in nowadays? It would be beneficial for us also for our future works and all.
You see, I would say the most dramatic application is nanotechnology for medical applications. Nanotechnology assisted cancer treatment. It's a very important area, sort of commercialized in many countries in the US. You can inject nanoparticles into your tumor, and the nanoparticles can be localized in the tumor area. Then you apply an external energy source. The tumor could be easily burned off. So nano for medical is increasingly growing or demanding. That's a huge area. Second important area is nano for environmental remediation process. Water purification, air purification. I showed you some good example. Nanotechnology for water purification, soil purification is increasingly important. It's a very big area. Third is nano for energy. Nano materials for fabrication of batteries, solar cells. Miniaturization is going on very fast. You make everything small using nanotechnology. So nanotechnology for energy is a huge area coming up. So these are some of the, that is why, we worked on batteries, we worked on EMI shielders. You see the mobile phone right now, what you use a mobile phone, if you open it, it's got a shielding material which is made of metal. Now we have taken a patent, you can make use of lightweight material. I showed you a couple of slides of my PhD student. So you can make mobile phones become lighter, and all electronic equipment need shielders. You can make beautiful shielders out of nanomaterial. This is for medical scaffolding applications. So number one is medical. This one, fine. Increasing application. I had a full PhD on nanoparticle assisted drug delivery for AIDS. The student is now in China. She actually connected AIDS vaccine to nanoparticle, and it was very nice for nanoparticle assisted drug delivery. You can load the drug at the right point.
Okay, sir. Thank you.
Thank you.
With your inputs and insights, good many are inspired to ask more questions. Most likely, I'll be sharing your contact details. Sometimes students will be able to contact you
Sure, Dr.
via
Binoy, I'll
mail
be
and
very
ask
glad.
questions.
If anybody wants to do project with me, they can
Yeah.
come to a Nano Center or some joint collaboration with teachers, submitting a proposal. We are very happy to support them.
See, that's something very wonderful for the participants.
And we are starting a company also in the campus now.
Okay, that is really great and very promising. I found, sir, your, what strikes me most is the scholarship. Certainly, secondly, the method of collaboration. Worldwide collaboration you have incorporated or invited, and you have also called upon the participants to collaborate with you in your lab, in your scientific explorations. This remains very promising for the contemporary times, and I am very sure the faculty, members of the faculty, scholars, youngsters, and the future researchers will be profiting a lot from this way of collaborative ventures with you and your team. And thank you so much for the wonderful contributions yourself and your researchers make to the world of science and technology.